and it's a good evening, and I'm so glad to be back under the stairs after last week. So welcome to Physics with Keith. It's our Tuesday physics tuition session, free, live to the nation, no to the world. And there's nothing else happening tonight that's of any interest, so this is the place to be. Hopefully you can hear me coming through okay. Hello, 𝘭𝘪𝘯𝘬𝘴. Hope I'm pronouncing your name correctly there. It's good to see you. If you are new here and you've never seen this sort of thing before, what we're doing is streaming straight through onto YouTube, and the link was put into Discord before. But look, if you're watching this and you can hear me, you're already on YouTube. So how do you type in Discord like all these fine people here? Well, there's a link to the Discord channel in the description for this live stream. You just click that, you get yourself signed up, and you can join in. Oh, Wombat, yes. No, this is definitely a soccer-free zone. I laughed with my wife earlier that I imagined the intersection on the Venn diagram between people who like football and people who are into physics is quite a small intersection. So I think we'll be okay for viewers, I hope. Today is going to be an exciting one. Today is going to be an introduction to special relativity. And me being the sort of person I am, where I usually immaculately plan for things, today I've decided to plan almost nothing. I've got a teeny bit here, but pretty much nothing is planned, so I'm sure this will go fine. I was away at the weekend on a retreat. It was wonderful, but because of that, I haven't had any time to do any planning. So I'm sure this will be fine. It's all going to come straight out of my head. Let's see. So what I'll do is I'll switch us across to the presentation screen, and the basic plan for today, I wanted to start by deriving three essential equations that we're going to be using in special relativity if you do special relativity at A level. And the course that I offer at my school has special relativity in it. So this is going to be useful for a lot of people because the one we do is, I think, the most popular A-level course that's offered. But if you do a different A-level and you don't have any special relativity, well, that's okay, because I think it is criminal that you can get an advanced level qualification in physics without having studied some special relativity. I just think that's wrong. So that's what we're going to do. This is for everyone. Now, if you're a GCSE student, you're thinking, oh, crumbs, what am I getting myself into with special relativity? I meant exam board, Pranav. Yes, I didn't mean options-wise. I was being a little bit flexible there with what I was saying to try to avoid pointing out that not many people study it. But thank you for picking me up on that. No, the GCSE, if you're a GCSE student, I'm going to show you that you don't need to be spooked by special relativity. It's counterintuitive, but it's accessible even to people who are not advanced level physics students. So hold on to your hats. We'll start with a derivation. And what I want you to do, we're going to start with a very basic thought experiment. Hello there, 𝘭𝘪𝘯𝘬𝘴. I think you're going to enjoy today. So a very basic thought experiment. Imagine, and this is the classic example, okay? So I'm not going to break any ground here with any new ideas. This is all the sort of the classic physics examples that we're going to be looking at. Let's imagine I've got a train. Here it is, a little choo-choo train. It's going to drive along. I'm not an artist, but I reckon that's pretty much a train. And let's imagine that there's someone on the platform watching as this train goes past. There's somebody on the train here. This person on the train is walking, and the train itself is moving. So a quick thought experiment. Let's imagine the train is moving at 10 meters per second. Let's imagine the person is walking relative to the train at a speed of 2 meters per second. How fast does the person on the platform, according to what you understand, basic physics so far, how fast does the person on the platform think the person on the train is moving? Go ahead and type it straight into the chat. We're starting nice and easy. Yeah, we're going to go with 12 rather than 10. Yep, 12 meters per second. Yep, so the train is moving to the right at 10. The person on the train is moving 2 relative to the train. So the person on the platform thinks that the person is moving at 12 meters per second. And you know what? That's what you would observe. If you were to get a stopwatch and a big tape measure and you do some measurements, that's what you would see. So for a very long time, that's what people thought reality was. We call this, the idea that you can just add speeds together like this, we call that Galilean relativity. Galilean relativity. Now, Galilean relativity was good from the time of Galileo right up until about the turn of the previous century, when there started to be some issues with it. And there's one experiment, a classic experiment, a famous experiment that was done by Mickelson and Morley, which proved that this isn't quite accurate. If both people are on the train, then the person on the train who's not moving relative to the train would think that the person on the train who is moving relative to the train would be moving at 2 meters per second. I don't have a problem with that bit. Okay, so the Mickelson-Morley experiment. This is how it works. No, apparently it's not letting me scroll. So here is me trying to be clever and use a different version of OneNote, and it's just as bad as the original. Well, we shall see, 𝗟𝗲𝗲. We shall see. It's not quite as simple as that. So, the experiment went like this. If I have a light source, here it is, and I shine some light, let's make it simple, let's make it monochromatic light. I shine some light so that it follows two different paths that are perpendicular to each other, and then I interfere the light from those two paths, then I should see a change in the interference pattern if one arm of this experiment is moving relative to the other. So let me just finish my diagram, and then this is all going to make a lot more sense. At the moment you're thinking, what is he going on about? So just hang fire. So let's just sort of set up the experiment. I've got a light source on the left over here. Light source. Dvorak, you are absolutely correct. Okay, so this thing on the left is a light source which is projecting light. Oops, let's get in the middle. Projecting light towards the. Can't quite get this where I want it to. Of course I can't. It's projecting light towards the right, and it reaches something called a beam splitter. And that's that black line there. What the beam splitter does is it sends 50% of the light up this way, and 50% of the light doesn't get reflected. It goes straight up. So that's what the beam splitter does. It's a very clever device. And then what we're going to do is we're going to place a mirror here, and we're going to place a mirror here. Let's pretend that's exactly on the end of that light. So we're going to have a mirror here, and we're going to have a mirror here. No, I don't think so, Dvorak. It's just semi-reflective. So if you take a glass substrate and you deposit very little silver on it, then it's not very reflective. You deposit loads of silver, it's very, very reflective. If you deposit just enough silver, then 50% of the light will go one way, 50% of the light will go the other. So it's a semi-reflecting mirror. So then what's going to happen with this mirror here, let's call this mirror here M1, this mirror here M2. The light that travels via M1 reflects back. The light that travels via M2 reflects back. Then we reach the beam splitter. So some of the light from M1, about half of it, is going to come down here to the light source. We don't care about that. That just goes back into the light source. But the rest of it carries on. So some of the light that went from M1 ends up going down this path here. And the same thing happens with M2. Some of it goes straight through the beam splitter. We don't care about that. Some of it gets reflected and goes down here. So we are going to get interference between the light that takes those two different paths. And you may remember from the wave stuff we did that when you get interference, you can get fringes appearing. So we set up the experiment very, very carefully, and there's loads I've not included here. Loads I've not included, like compensating plates, why we need to have collimated, monochromatic, coherent light sources and things like that. There's loads I'm not including here to keep it simple. No worries, Lex. You don't need to apologize. This is optional. So the light that comes here is going to interfere, and you're going to end up with an interference pattern. Now, the idea is that if the light travels in the same direction that the Earth is moving, so if the Earth is moving in this direction, this is the direction of the Earth, so the Earth has a speed, let's call it v subscript e, then the light that's traveling to M2 is going to take longer to reach the mirror, because the Earth is moving, so the mirror is moving away as the light is traveling towards it. Now, the light that just goes to M1 doesn't quite take as long. So the optical path length to M2 is longer, which means that we're going to get a certain interference pattern. If we rotate this apparatus around in some direction, let's rotate it in either direction, it doesn't really matter. As you rotate this apparatus around, then all of a sudden the longer optical path length becomes M1, and there's a transition between the two. Now, according to Galilean relativity, going back to the train example, if person 1 is holding a torch and shines light in this direction, then one of two things can happen. Either the light gains the speed from the train, or the light doesn't gain the speed from the train. If the light gains the speed from the train, then the person here should see the light travelling faster than the person here. If, however, the light doesn't gain the speed from the train, so the light is travelling at a certain speed relative to this person, then the light will appear to be going slower from this person's point of view. Either way, each person should observe a different speed of light. So that's Galilean relativity. It works for people running on trains and people throwing balls on trains, all the rest of it. Does it work for light? So we go down here. Mickelson and Morley did the experiment. It didn't work. There was no change in the interference pattern. There was no evidence whatsoever that the speed of light was influenced in any way by the speed that the Earth was moving through space. What that means is that the speed of light is completely independent of the speed of the things that are moving, the observer and the thing that emitted the light. Completely independent, which is really counterintuitive. So what I'm going to do, I'm going to draw a diagram. We're going to derive this together. I'm going to draw a diagram. I'm going to imagine a rocket ship. Well, that's the point there. It's not absolute. Let's go with a rectangle. So here's my rocket. Oh, it's gone red. Doesn't matter. Here's my rocket ship. Okay, clearly a rocket ship because it's got a point on the end. Okay. Can I change my color of my pen? Apparently I can, but I have to use my mouse. I don't know if that's worked or not. We'll find out. No, it's still red. Look at that. So I started using a completely different version of OneNote, and it's equally as glitchy. Look, okay, let's get that pen, that one there, and can I write with it? There we are. I'm back to black. Sort of, but yeah, sort of. So what we want to imagine is that this person here is doing an experiment. And in this experiment, what they are doing is they've got a light source here and they've got a detector here. And very simply, they are shining. I want to use this one. I want to use that pen. Let's see if that works. No? You see what I mean? It's frustrating, isn't it? No one has yet designed a drawing tablet piece of software that actually works. It's 2022. No, it's not. It's 2021. We still don't have it. Astonishing. Anyway, so the person here is shining light. In their reference frame, it looks like the light is doing this. It's just going from there to there. It's traveling a certain distance. And they time it. They've got a stopwatch. So let's go back here. Let's do it manually. Let's make it a bit thinner. So they've got a stopwatch. There's a stopwatch. And they time how long it takes for the light to get from A to B. And when they time it, they get a certain amount of time and they're happy with that. However, there's also a person stood on the ground, just as we had before. So here's our person stood on the ground. And that person stood on the ground is also watching and timing how long it takes for the light to travel that distance. However, the person on the ground can see that the rocket itself is moving. I mean, if you imagine the rocket was moving in space and had no windows, you would have no idea that you were moving if you're going at a constant velocity. That's Newton's first law. So the person on the rocket ship has no idea they're moving. And they do the experiment, the light goes in a straight line, they're fine. The person on the ground doesn't think the light goes in a straight line. The person on the ground thinks that the light goes diagonally. Because the light is moving. The whole experiment is moving. So they see the light going diagonally, and they time how long it takes for the light to go that distance. Happy so far? Probably. I'm going to get some terminology now. The person who's moving with the experiment, so they think the experiment is stationary, they measure the time it takes for light to travel that distance, and we're going to call that T0. T0 is what we call the proper time. Doesn't mean it's any more correct than any other time. We call it proper time because it's measured in the same place, what we call reference frame, as the experiment. This person down here just measures the time. And the whole thing is moving. Now, what we do know is that the light speed, according to the person on the rocket ship, is measured to be c. And the light speed, according to the person on the platform, has to also be c. That was what Mickelson and Morley's experiment showed. The speed of light was invariant. It didn't matter. So I'm now going to draw this diagram slightly larger. Hopefully you're keeping up because I'm about to get you to answer some questions for me. Here's a slightly larger version of the diagram. Here is the light path as observed by the person who is not in the rocket ship. And here is the light path as observed by the person who is in the rocket ship. Hi, 𝗭𝘁𝗧. And this is the path of the rocket. And we're going to make this vector diagram displacements. Displacements. So if these are displacements, we can start with the easy one. The rocket is only moving as measured by this person here. So what is the distance, I should try again, what is the displacement of the rocket in a time t? What do you think? Rocket is moving with a velocity v, and we time how long it takes to move with a stopwatch that's not on the rocket. So what's the displacement? Vt. Yeah, it's as easy as that. Vt. Okay, next. Yeah, perfect. Next. This arrow here. This arrow here is the displacement of the light as observed by the person on the rocket ship. The light travels at a velocity of c, and it takes t0 seconds to go from here to here. What's the displacement here? CT. Absolutely right. CT0, sorry. Yep, thank you. Who corrected me? Mateus and Wombat. Thank you very much. I'm glad you corrected me. Because the stopwatch, well done, Pranav, the stopwatch we were using to measure the time it takes to get from A to B in the reference frame of the person on the rocket was T0. So it's CT0. Right, thank you very, very much for that. So what is it going to be for this arrow? The displacement of the light in the reference frame of this person here. What's it going to be? Says several people are typing. That's good. CT. Okay, so it looks like Pranav has gone straight to Pythagoras. Hold your horses there. We're coming to that. You've anticipated exactly what I was doing. No, Wombat, you were right. Wombat, you were right. We're now going to do what Pranav wanted to do. So here is our diagram. It's a vector diagram with 3 displacements. I'm just going to move it over here so I've got a bit more room. We are now going to find out what t is. Its relationship to t0. That's the next step. So we're going to go through some stages. What I'm hoping is that you'll join in with me, and that you'll tell me the steps. So what's the first step if I'm going to do Pythagoras? What's the first step, do you think, to combining all these? See, Pranav's mistake is he didn't actually put an equal sign. So he hasn't actually written an equation. No, Dvorak, you see... Oh, I see. You're saying CT equals that. Yeah. So the first step, this is what I would say is the first step. CT all squared. That's this length squared equals CT0 squared plus VT squared. You see? Now, I know what you're thinking. Is C a vector? Because what we've got here is a diagram where this purple arrow here, it's gone off the screen a little bit, this purple arrow here, and this purple arrow, I can't move it with this, this purple arrow here, and this purple arrow here are in different directions. T doesn't have a direction, does it? And yet the C part is the same C. So I know what you're worried about. The directionality is handled by the arrow, not by the symbols. So don't get too concerned about the fact that C looks a bit like a scalar, and yet we're about to do Pythagoras on it as though it's a vector. You're going to get used to that. There is some mathematical sleight of hand I'm going to do a little bit later today that relies on you overlooking that a little bit. And if you're really interested in how it works, you're going to have to study quantum physics, actually. Right, so the next step, what do I do next? I want to know what T equals. T equals something. So what am I going to do? Just tell me what to do and I'll do it. I want T as the subject. What do I do? And this is GCSE students. This is rearranging equations, so you can join in as well. Get T on one side. Yeah, but how can I do that when there is a T here and there's a T here? So what do I do? Square root? Not yet, 𝗬𝘂𝘶. What I'm going to do is this. Yeah, expand the brackets, which I think is what I've just done there, Charles. Then factor it out. So we subtract. You can't factor it yet. Let's subtract that from both sides. So c squared t squared subtract v squared t squared equals c squared t naught squared. So far, so good. Now we can factor out the t squared. C squared minus v squared equals c squared t naught squared. Now we can divide through by this mess here, and we get t squared equals c squared over c squared minus v squared t naught squared. Yep. Now, some very bright people will probably already know how to simplify that. But I'm going to cut a step here because I'm a fairly lazy individual in order to simplify that. I'm going to divide the top and the bottom by c squared. So if I divide the top by c squared and divide the bottom by c squared, I'm going to end up with just the same fraction, aren't I? So c squared divided by c squared is? What's c squared divided by t squared? Try again. What's c squared divided by c squared? 1, yes. Okay, now let's do to the bottom bit. What do I end up with? 1 minus v squared over c squared. I know, I'm going quite fast because I just noticed the time, but we're nearly there, actually. Look, we're nearly there. You were close, Lex. The last step is to take the square root of everything. Yeah, there we go. Square root of 1 minus v squared over c squared. And that's multiplied by t0 squared. So what is this? We can actually make this look a little bit easier. In fact, I don't like the square root like that. So I'd probably put the square root just on the bottom bit. But what we can say, we can simplify this a little bit so we don't have to keep writing this each time. We can say that gamma equals 1 over the square root of 1 minus v squared over c squared. So it's a little bit... Oh, yes. Thank you, Pranav. That's me and autopilot. Thank you for that. So this can be simplified as just t equals gamma t0. What does that mean? Well, just have a look at that gamma factor. Yeah, you got it, Dvorak. You got it. No, I can see it. I can see it. So that gamma factor, if v is small, much smaller than c, then this term here is, you know, pretty much 0. And 1 minus 0 is pretty much 1. And the square root of 1 is 1. And 1 over 1 is 1. So gamma equals 1. And so the time measured by this person here would equal the time measured by this person here. And that's what you observe for small speeds, everyday speeds. But if you start increasing the speed, if you start going up to relativistic speeds where gamma becomes a significant number, maybe, you know, 1.5, 2, 2, 3, 4, 5, 6, and so on, then all of a sudden we're getting different times. Now, this is the bit that's going to mess with your head a little bit. We did the whole experiment imagining that this person here is not moving, and this person here is. But from the person on the rocket ship's perspective, they're not moving, and the person on the ground is. And T0 is always where the clock is measuring the actual phenomena that's stationary. So if the person on the ground is stationary and the person on the rocket ship is moving, then that's T, and that's T0, and that's T. And if you consider it the other way round, like we did in this example, then they're the other way round. So proper time is the time measured on the reference frame that is not moving. They can be if they're not moving relative to each other, if the rocket ship was stationary. Now I want you to consider something. Yeah. Imagine I've got a race. And here's the starting line. The person on the rocket ship measures T0 because they are on the same reference frame as the experiment. So the stopwatch is not moving relative to the experiment. So that measures proper time. The relativistic time, T, is measured by the person who's watching the experiment move. So we're going to have a race. There's the starting line. There's the finishing line. Okay? And there's a distance between those two. The distance between those two, that is working now. The distance between those two, let's just call it L. In fact, let's call it L0. Because I can lay my ruler down, my tape measure down. Between S and F, my tape measure is not moving. In order to measure the time it takes for a person to run from here to here, I have to move the stopwatch from here to here. I have to move my stopwatch in order to measure the time it takes to move from the starting line S to the finish line F. Dvorak, you are absolutely correct. So I am only able to measure relativistic time. The stopwatch is having to move. You know, the experiment is here. The stopwatch is moving. I have to measure relativistic time and what we call proper length if I want to know how fast this person has gone. The speed the person has gone is L0 over T. Alternatively, we could consider the person to be stationary. If the person is stationary, then their stopwatch is not moving. They are going to time how long it takes them to move. Well, actually, they're not moving. They think they're staying still, and the entire universe is moving in the other direction. So they would see that there's some distance between the starting line and the finish line. And the distance they would measure is a moving distance. Because they think they're stationary, that distance is moving. So they would measure L. So similarly, the speed that the finish line and starting line move is L over T naught. It's absolutely critical that you realise that the speed is the thing that they agree on. The speed of the person moving through the stationary reference frame that I've drawn here in green, or the speed that the starting and finish line move in the reference frame that I've drawn in blue, where the person isn't moving. The entire universe is moving in the opposite direction. Right. Well, I want to get an equation for L in terms of L naught. I want L, and I want to know how it's related to L naught. What do I know? T is equal to gamma T naught. You derived that yourself using Pythagoras. You derived that. And we will do some questions on this. We will. We just need to get through some of these basics first. The derivation is good. It's good physics. So using what's highlighted here on the right, and using the expression for T, can you derive an expression for L as a function of L0? How L relates to L0? If you're a GCSE student, remember, look, you've not actually seen anything here that's beyond you. Pythagoras you've seen before. All you've got to do is get your head around the fact that the speed is the thing that people agree on, not the distance, not the time. We don't agree on that. That doesn't make one time correct and the other one incorrect. We just have different times and different lengths. We need a gamma in there. Yeah, so is there any way you can shove a gamma into that? Wombat. So look at your expression. T naught over T, what does that equal? Dvorak, not quite. Have a look at Wombat's expression there. Yep, 𝗭𝘪𝘯's got it. 𝗭𝘪𝘯's got it. So what we can do, we work with Wombat's example. Wombat took this, and Wombat said that L equals T naught over T multiplied by L naught. We know this expression here, T naught over T is equal to 1 over gamma. Oops, that's a funny looking gamma. So we can plug that in over here, and we end up with L equals 1 over gamma L naught. Yeah, exactly. So what this means is that, can you see the steps, Mateus and Dvorak? Can you see the steps? It just went from here to Wombat's expression here, and then substituting in time, what we call time dilation, to calculate length contraction. Yeah. So we call this expression time dilation because we're multiplying time by a number that has to be bigger than 1. Look at gamma. Gamma can't possibly be bigger than 1. I'll scroll up to show you what gamma was again. So gamma there cannot possibly be smaller than 1. Gamma has to be bigger than 1 or bigger, going up to infinity as v approaches c. If v was equal to c, then this would be 1. 1 minus 1 is 0. And we'd end up with something 1 divided by 0, it's undefined. But if v is very close to c, then this number here becomes very close to 1. So this number down here becomes very, very, very small. And so gamma becomes very, very large. Yeah, Dvorak, yeah, but it depends on your reference frame. And this is the key thing. So if you look at the race example, the person racing, their clock appears to be running slower for the person who's not racing, who's watching the race. So if the person running said hello as they ran past, the person who's watching the race and not running would see them running and saying in slow motion, hello, if they ran fast enough. But the person running would then get a reply, and the person who's not running would then say hello back. And the person not running, they're not moving in their own reference frame, so they just think they talk normally. This person thinks that they're stationary, and the person here is moving backwards. You think you're stationary. In which case, this person would think that the reply is in slow motion. They each think that each other is in slow motion. I've got one more derivation, then we can get cracking with some questions, and I'm really looking forward to these questions. For the questions, by the way, I'm not going to ask you to calculate gamma loads of times, because that's just grunt algebra. That's just plugging numbers into this gamma factor, and you can do that. I know you can all do that. I'm going to use gamma equals 2 and then pick some funny examples to see if you can figure out what's going on. No, Pranav, because there's no way in movies anyone will be able to move fast enough. No, Pranav. So plug in what we would call what would we call them? Macroscopic speeds, perhaps is the wrong word for it. Just plug in some mundane speeds into that equation where c is the speed of light into the gamma equation and see what comes out. I don't know, pick 100 meters per second. Yeah, okay. Well, we're edging on the edge of realism there now, aren't we, Dvorak? So I'm going to say probably not for the Flash. Okay, we've got one more derivation. This is an exciting one. This is an exciting one for me because this is the derivation I very rarely do for my students. Usually time is of the essence at school. We do the derivations you've just seen, although it takes 3 lessons to do them. I don't know why. Taking us 37 minutes. The last derivation is what happens with mass. Now, there's always going to be someone who gets in the comments section and comments, there's no such thing as relativistic mass. It's just mass. Relativistic mass is an illusion. Okay, fine. All of physics is just a model. It's just an engine that we plug numbers into and get an answer out. And we compare that to reality and see if our model works. So the model I'm using, I'm going to call it relativistic mass. If you don't like that, okay, that's fine. Don't call it relativistic mass then. Tie yourself into knots finding a different way of describing it. But I'm going to call it relativistic mass. So let's start with the world's most famous equation. Finish that equation for me, ladies and gentlemen. The world's most famous equation. Yeah, E equals mc squared. Of course it is, except it's wrong, isn't it? It's not quite right. It'd be better if I wrote down something like this, where E is the rest energy. Oh, Dvorak went with a classical physics. He's not wrong. He's not wrong. Classical physics. It is a model that works in a certain paradigm to as many significant figures as you can measure. It doesn't make it wrong. It just means it's not the most accurate model. What makes you think that the model I'm about to show you here is right? It just happens to be more accurate under other paradigms. So m0 is the rest mass. If you've done any particle physics... No, sir, when you said general relativity was not that correct. I don't understand what you're asking me there. Your wrongness was wrong. Yeah. No, general relativity is a better model for how gravity works, but that doesn't make it necessarily truth. I don't know what I'm doing. No, nor do I, 𝗟𝘳𝘳. Oof sign equals large. Always be wary of the oof. Okay, we've only got 20 minutes. I'm going to have to focus. So That's rest mass. If you've done any particle physics, you'll know that if you take antimatter and matter, which both has mass, you can annihilate them and you get an amount of energy out equal to this. Well, actually, that's not quite true, because if the matter and antimatter are moving, you actually get more energy out, obviously. So there's another equation here. E equals hf. That's the energy of a photon, for example. Now, photons don't have any mass. So if we want a more general equation for the energy of a particle that takes into account the energy it has when it's not moving and the energy it has when it is moving, we need to find a way of combining these. Now, I'm going to use a subscript here, m, to indicate moving energy. That's not a terminology I've ever seen anywhere else. So I'm going to go with it anyway. C equals F lambda, so this just becomes hc over lambda. And we know that lambda equals h over p. That's de Broglie's hypothesis. De Broglie's hypothesis that there are something called matter waves. And the wavelength of that matter waves is inversely proportional to the momentum. Yeah, that sounds more physicsy. Yeah, we'll go with that. So what I want you to do is put all this together and get an expression for the movement energy, or the energy of motion, in terms of, or let's say P and C. You should be able to do that. The energy of motion in terms of, let's go with P and C, for a particular photon, for a massless particle. As do I, 𝗟𝗵𝗸𝗀, as do I. GCSE students can do this. Yeah, but I want it in terms of P and C. It's as easy as that. Yeah, 𝗭𝘪𝗯 and Matthias have got it. It's as easy as that. Don't overcomplicate it. So, Pranav, look, if we substitute for lambda, h over, just like Wombat has done. There we are. I won't bother doing it. Just do what Wombat just did. So you end up with CP. Or I'm going to put PC because I'm feeling funky like that. Now, the problem with that is P is momentum, which is a vector. So I don't like the fact it's a vector. So I'm going to cheat a little bit here. A little bit of mathematical sleight of hand. I'm going to square everything. I know what you're thinking. So I've got a real problem with this because you had a scalar equals a vector. Well, now I don't. I've fixed that problem by squaring things. Okay, but a mathematical sleight of hand. If I was a magician, I'd have done that whilst trying to distract you with something else. Okay, so what I'm going to do now is I'm going to say that the total energy, as people are typing, the total energy should be the energy of these two added together. However, because I've got a bit of mathematical sleight of hand here, I've got something funky going on with vectors. Energy's not a vector, but actually, again, mathematical sleight of hand, I'm going to treat it as though it is. So when I add these together, I'm going to add the squares of these together. So this squared is this, and this squared is this. So I'm going to add those two together. We now have an expression that says the total energy, remember it's energy squared, it's not actually energy, is going to be P squared C squared plus m0 squared C to the 4. That expression falls out of quantum physics. In fact, you've just seen it fall out of this, but it falls out of quantum physics as well. It's a beautiful expression. Consider a particle with no mass, like a photon. A photon, if you consider a photon, you end up with this expression. Oh, that was supposed to be a highlighter pen. Once again, one note is broken, this time in an altogether different way. So you end up with this part here. If the mass is 0, you end up with the energy of the photon being equal to PC, and you get straight back to the start again, which is exactly what we thought. So if we've got a massless particle, this works. If we have, however, a particle with mass that's not moving, then PC is 0 because we're not moving, and we end up with this part, which, again, when you square root it all, falls back down to the rest energy. So it does work. Okay, this expression does work. When you combine those two energies, you end up with this. Now's where it gets really fun. So I'm going to do the rest of this derivation. You've derived to this far. You helped me out with it. So now we're going to move on to the rest of this derivation. P squared. In fact, I'll write this next to it. P is equal to mv in classical physics. So P squared will be equal to m squared v squared in classical physics. But notice this is a different m. So this is an m when things are moving. This is an m when things are not moving. They are different masses. So this mass over here could well be relativistic. Well, let's find out. So I'm now going to substitute that in for p squared. And this expression becomes m squared v squared c squared plus m0 squared c to the 4. If you're playing along at home, do play along. Don't just sit there watching it. Or sit there, it's up to you. Sit there and watch it if you like. The next step, and this is again a clever little step here. So I'm going to put this in brackets because it's a clever little step. E for things moving would be mc squared for things moving. So E, a moving energy, is m, a moving energy, c, a relativistic mass, c squared. We're going to say that's true. We're just going to say that's true. That's E equals mc squared when things are moving. Well, if that's the case, then E squared is going to equal m squared c to the 4. Well, c to the 4 is just c squared. Why on earth did I write that? Because that way I can rearrange that expression to get m squared c squared equals e squared over c squared, which I can then, hear me out, substitute in here to get e squared. Yes, it is, isn't it? Thank you for that. Whoop. There we go. I'll put that bit in brackets because it's a clever little bit there. So we end up with e squared over c squared, e squared over c squared, and then v squared. So I'm going to show you which bits I've done here. M squared c squared is m squared c squared, and I've replaced that with e squared over c squared. So algebraically, there's no issues there. They're not cheating or anything. And that's plus my m0 squared c to the 4. And that's all still equal to energy squared. So next, I'm going to subtract this part from both sides. I end up with e squared minus e squared over c squared v squared equals m0 squared c to the 4. I'm not done yet. Then I'm going to factor out the energy. So e squared 1 minus v squared over c squared. Now some people are going to start going, hang on a minute. That looks jolly familiar. Where have I seen 1 minus v squared over c squared before? So then what I'm going to do is I'm going to square root everything. E square root of 1 minus v squared over c. Oh, this looks very familiar. And we've just decided before that E was equal to mc squared. Look, that was just at the top of the screen there. E equals mc squared. So we're now going to use that in place of this E here. So we end up with mc squared multiplied by the square root of 1 minus v squared over c squared equals m0 c squared. Can you see what I can do with the c squared? Bonk. Bonk. It's not gamma, it's 1 over gamma. It's 1 over gamma, Dvorak and 𝘬𝘬𝘀𝘀. This is m equals 1 over this. That's gamma. That is gamma m0. That was a hell of a derivation, but it was great fun. So what we've just shown using, let's face it, the algebra wasn't tricky. Not really. We started with some bits at the top, E equals mc squared, and that second equation here, E equals hf, and the third equation, de Broglie's hypothesis, you learn those in year 12. You learn those in year 12. We've just used those and some basic physics, put it together, and derived this expression here. So what we now have are three equations, and that's what we're going to use in the last 10 minutes. We've got that relativistic time is gamma multiplied by proper time. That's the first one. We've got that relativistic length is equal to 1 over gamma multiplied by proper length. And finally, we've got that relativistic mass is equal to gamma multiplied by rest mass, which I suppose you could call proper mass, but no one does. And remember that the proper measurements, the ones with the zero subscript, are when measured in the reference frame of the thing that thinks it's stationary. So, let's do this. In all of the examples I'm going to do now, there is motion. And in all of the examples, to make the maths easier, gamma is going to equal 2. We're not going to bother trying to solve gamma. It's just plugging numbers into an equation. We're just going to say gamma equals 2 for everything we're about to do. Okay? I have seen that, 𝗟𝗲𝗲. I have seen lambda used instead of gamma. I've also seen beta used. The exam board that we follow, we tend to use gamma, which is, you know, a Greek letter G. After, well, let's say Galileo. I don't know why. Right. So it's a rude gesture towards Galileo. So here's our first example. Here is a rod. I use AQA Examiner. Here is a rod. Yeah, that'll be why. The rod's length is 2 meters long. Nice and easy. I am moving in a very special rocket ship such that my gamma factor is equal to 2. Starting with the easiest of questions, how long do I observe the rod to be? One meter, there it is, 1 meter. Length is always contracted. Length is always, always, always contracted. So let's do a second example. Here we go. Again, this is some basic examples. Things will get much more complicated next time. So here's a rod. And I measure it as I fly past in my rocket ship. Here I am in my rocket ship. And I've got a ruler, which is stationary relative to me. And it just so happens, I've not drawn this to scale. The ruler, when I measure it, is the same length. I'm moving, again, with a gamma factor of 2. And I measure that rod here, this rod that I'm measuring, to be 2 meters long as I fly past. So how long is the rod? Of course. I mean, it's so obvious, isn't it? When I say it like this, you think, well, yeah, it's easy. It's 4 meters, because what you are measuring is the contracted length. You're measuring L, not L0. It really is as easy as that. So now let's look at some times. Let's imagine I am the classic example now. I'm going to go for the classic example. I've got a particle detector here, and I've got a particle detector over here. And let's imagine that the particles decay. And the half-life of the particles is, let's say, 10 seconds. Let's just say. It's probably a really bad idea having that sort of time because I haven't actually checked my numbers. But let's just go with 10 seconds. That's the half-life. And let us say that half of the particles that go through here, so I detect my activity here, whatever it is, let's call that A1. Let's say that A2 is actually equal to half of A1. So half of my particles have decayed as they've passed between these two. So how long has it been between these two? Well, what's the time between these two? That's the first question. What's the time that has expired from passing through the first one to passing through the second one? So we got some different answers. Pranav, Wombat, and Matthias say 20 seconds. Dvorak says 10 seconds. So the particles are moving. Because the particles are moving, their time, that 10 seconds in their time between here and here. That's 10 seconds that they measure. But when we measure it with our stopwatch, they're moving. So we think that things are going in slow motion. That an event that would usually take 10 seconds is now going to take 20 seconds. So our relativistic time, which we're measuring, would be 20 seconds. The particles clock, which is moving with the particles, has taken 10 seconds because half of them has decayed. The particles clock measures T0. No, the particles are moving. The particles are moving. Yeah, absolutely. The particles are moving. And that can be a sort of a tricky thing to get your head around that. The particles are moving. Right, good. I'm just going to get rid of these for a second. So, no, it's not silly you. It's a tricky concept. So now what we're going to do is the same. We're going to do the same sort of thing. We're going to have a detector here. A detector here. Oops. There we go. The distance between those two detectors, there we are, is, let's say, 100 meters. Drop that off. Particles are moving through it like this. The particles are moving through it. Again, gamma's like this. So how far apart are the detectors in the particles reference frame? Don't overcomplicate it. How far apart are the detectors in the particles reference frame? $50 meters. Absolutely right. It is 50 meters. Of course it is 50 meters. So the reason why this all checks out is because length is contracted as time is dilated. The two go hand in hand. That's how this checks out. From the particle's point of view, it hasn't gone as far. But from our point of view, the particle's clock has been running more slowly. Okay, it's just hit 7 o'clock. Now I have got a drill, which we can use a little bit at the start of next lesson on this exact example. That comes later, Pranav. Don't worry, that comes later. So we're going to put a pause on this. We'll pick this up next week. We're going to pick it up straight away with some examples where you have to apply special relativity. Then, in the second half of next week, we'll look at Lorentz transformations, Minkowski diagrams, and a few paradoxes if we have time. A really exciting end to Season 4 of Physics with Keith. Have you enjoyed it? I think it was fun, yeah. Not so much interaction today, but I think it was fun. If you want to, help me out, maybe. It does help me. I don't know how it helps you, but it definitely helps me. Click on like and subscribe. Yeah, Dvorak, we'll be looking at world lines. We'll be looking at the lack of absolute simultaneity. We'll be looking at all sorts. Yeah, this is what makes physics fun. This is what gets people excited about physics. It's weird. And the thing that's going to melt your brain is that it's the most accurate picture, the most accurate model we've got. It works, even though it's weird. Right, I'm going to have to stop there. Because I'm quite hot under these stairs. Oh, Dvorak, you flatter me. Please tell all your friends and maybe write to my headmaster so I can get a pay rise or something. Ha ha ha, I'm joking, maybe. I'm going to go before I say something else I will probably later regret. Weirder than quantum physics? Dvorak, we used quantum physics in deriving it. So it's equally as weird. Everyone have a lovely evening. Have a lovely week. Stay very safe. Thank you for tuning in. I'll see you next week for the final episode of Season 4. Take care of yourselves.